guys, welcome back to my channel. Please remember to like and subscribe. Today we're going to be talking about the Argon diagram and the polar form of the complex number. Now let us start by looking at the rectangular form or the Cartesian form of the complex number. This form is z equal x plus I y, where x is the real part and y is the imaginary part. Now this complex number can be represented as a coordinate form or as an ordered pair. So as an ordered pair, we can have this complex number being represented as x and y. We can also think of it in a similar way that we think of a position vector. And normally a position vector is represented with respect to the origin. So probably I could look at it as x and y. Now, graphically, a complex number can be represented on what we call an Argon diagram, developed by a French mathematician known as Jean-Robert Argand. Now, on my Argon diagram, similar to the Cartesian plane, we have two axes. Difference being is that the horizontal axis is what we call the real axis. So I can call this re z. And the vertical axis is what we call imaginary axis. I'm going to call this im z. Now, x and y can be thought of as a coordinate, where x is on the real axis and y is on the imaginary axis. So imagine if I were to have x here and y some point here, then this ordered pair would be a point right here. I call it z. Now, if I'm thinking of it as a position vector, I could connect it to the origin. So here we go, better defined, we call that z. Right? So there are two axes, the imaginary axis and the real axis. And similarly to how we look at the concept of vectors, we can also apply it to the concept of the Argon diagram and the representation of a complex number. Now we're going to look at about 3 examples to see how we represent them on an Argon diagram. So here's our first complex number, a, which is 2 plus 3i. So I'm going to look for 2 on the real axis and 3 on the imaginary axis. So they would meet at this point here. So I'm just going to connect that to the origin so you can see it clearer, and probably I could call this z1. My second complex number is negative 4 plus 2i, which means negative 4 on the horizontal axis and 2 on the imaginary axis. So negative 4 here, 2 there. We can connect that to the origin as well. I'm going to call this z2. And my final complex number, which is negative 3 minus 3i, so I'm looking for negative 3 on the horizontal, negative 3 on the vertical, which is about here. You can also connect that to the origin. I'm going to call it z3. Alright, so we can look at them as position vectors. Now, a part of our investigation, what we want you to do, we're going to make the video later on, but what we want you to do is to plot z1 plus z2, find the sum of them, which is z1 plus z2, and plot the result and see what you observe, and also do it for subtraction and multiplication and write down your deductions, right? So we'll come back to it later on. Now we're going to go into what is called the polar form of the complex number. Now, just like how the complex number has a rectangular form or a Cartesian form, it also has a polar form. But to develop the polar form, we're going to start out with the Cartesian form, which is z equal x plus iy. Now let us take this and put it on an Argon diagram. So draw my Argon diagram. Let me put my complex number. Let me say that this is x, this is y. Now, once I've represented the complex number, which is z, I can actually form a right angle triangle out of this. Now, bear in mind that this is the real axis. The complex number itself will form an angle with a positive real axis. I'm going to call that theta. Alright, notice it will also have a length I'm going to call, which is a module, which we call a modulus. Let me put this here. Now, there's a special name given to theta. Theta is what is known as the argument. Alright, I'm going to label the hypotenuse here, and r here is what we call the modulus. Now, let us start with the modulus. if this is x and this is y, we can actually find r by using Pythagoras' theorem. So we can say that the modulus, and I'm going to be using the modulus symbol, of z, which is equal to r, is equal to the square root of x squared plus y squared. X being the real part and y being the imaginary part. Going back to this, we can also look at the argument. Now, we know the imaginary part and we know the real part, so we have the opposite side, which is imaginary, and we have the adjacent side, which is real. That brings us to tan. So we could actually say that the tangent of theta is equal to y over x. So we can say that theta is equal to tan inverse y over x. Or we can say tan inverse the imaginary part over the real part. And we shorten this. Theta is what is called argument. So we shorten it by saying arg theta equal. Now, sorry, not arg theta, but arg z. So the argument of z is equal to theta, which is equal to tan inverse of y over x. Now we can, once we have these, we can now talk about what we call the polar coordinates. So my polar coordinates would be r and theta, written in that form. Now, where this particular syllabus is concerned, we don't only talk about the argument, we talk about what is called a principal argument. Let me go down a bit. We use what is called, let me change the color here, the principal argument. And the principal argument, theta, is between negative pi and pi. And we could probably say, since negative pi and pi will probably take us to the same, well, it actually take it to the same place. We probably could remove the equal to sign there. So we could say theta is greater than minus pi, but less than or equal to pi in this particular scenario. Now let us look at some examples of how we find the polar coordinates. All right, here's our first example. Find the polar coordinate of 1 plus I. Now to make this simple, the first thing I would want to do is to put this on the Cartesian plane. So I'm just to quickly do a thing here. It's 1 plus I, so it means it's going to be in the first quadrant. So I'm going to have one on the imaginary axis, one on the real axis. So something like that. Theta here. So let me just say re, and this is my imaginary axis. Now, let's start out with the modulus, and don't forget that this is a right angle triangle, and this is why this is applicable. We can say that the modulus of 1 plus I would be the square root, and of course it's 1 in the real direction, so 1 here, and 1 in the imaginary direction. So I'm going to have 1 square plus 1 square, which is really equal to root 2. So we agree that the modulus is equal to root 2. The argument of 1 plus I is equal to tan inverse the imaginary part over the real part, so that's 1 over 1, which in this case is going to give me pi over 4. So my polar coordinate would be root 2 and pi over 4. Alright, when it falls in the first quadrant, it's pretty straightforward. Now let us look at when it falls in another quadrant and see what happens. Now let us say that the complex number was 1 minus I. It means that the real part would be 1, but the imaginary part would be negative 1. So I'm going to have 1 on the real axis, negative 1 on the imaginary axis, which means that my complex number is going to fall here. Alright, bear in mind that the argument is formed with the positive real axis. So let me just complete the triangle here. So here I would actually have 1 in that direction, 1 in that direction. So I'm going to put 1 here. Because I'm going down, this is going to be a negative 1. Now the modulus of 1 minus I would be equal to the square root of 1 square plus negative 1 squared, which is also equal to root 2, just as in the previous question. The minus sign doesn't impact the modulus. All right, we're looking at the absolute value there. Now, what about the argument? The argument of 1 minus I would be equal to tan inverse the imaginary part, which is negative 1, over the real part, which is 1, which is going to give me minus pi over 4. Now, this is indeed correct, because if we were to look at this, since we said that the principal argument is between pi and negative pi, we definitely couldn't go anti-clockwise. If we were to go anti-clockwise, we would have to pass 180, which is pi. I would also have to pass 270, which is 3 pi over 2. So it means that we now have to go clockwise, because we can't go beyond pi or minus pi, which in this case is minus pi over 4, as you can see. So my polar coordinate would be root 2 with a minus pi over 4. Alright? Now these two quadrants are pretty straightforward. The first quadrant and the fourth quadrant. Whatever you get when you use your calculator will be the correct answer. That will be pretty straightforward. Let us look at what happens when it falls in either the second quadrant or the third quadrant now. My third example is negative 1 plus I, which means it's going to be negative 1 on the real axis and 1 on the imaginary axis, which means it's going to fall in the second quadrant right here. So let's see what happens. Now, bear in mind that the angle is formed away from the positive real axis. So here I'm going to have theta. But just for argument's sake, I'm going to put alpha here, because that is what you're going to get inside of a triangle. So let's go with a modulus. The modulus of negative 1 plus I is going to be equal to the square root, negative 1 squared plus 1 squared, which again is going to give me root 2. All right, pretty straightforward. The argument of negative 1 plus I is going to be tan inverse 1 over negative 1. Now, but in this particular scenario, we have to be very careful, because whatever we do here, what if we were to put this directly into the calculator, what I would actually end up with is alpha. All right, so I would necessarily get the angle that I want, and alpha would be that very small angle there. So what I'm going to have to do is that to whatever I get here, I'm going to have to add pi, because this complete from the real axis to here would be pi. So I'm going to have to add pi to this. So this will be plus pi to get my theta there. So this becomes minus pi over 4 plus pi, which is going to give me 3 pi over 4. So my polar coordinate would be root 2 and 3 pi over 4. So what do I do in this particular scenario? When it falls in the second quadrant, what we have to do is to add pi to whatever we get from our calculator, because we're going to end up getting a negative angle, which in this case is minus pi over 4. We add that to pi, which gives us 3 pi over 4. All right. Or you can simply use your diagram. Clearly, this angle here is going to be pi over 4. The entire thing is 180. From the positive real axis to this axis here is 180. So we simply subtract pi over 4 from 3 pi, no, from pi, which gives me 3 pi over 4. Right? So you can either use a diagram or you can use this technique. All right, for our fourth complex number, negative 1 minus I, that's negative 1 on the real axis and negative 1 on the imaginary axis, which means it's going to fall in the third quadrant. So it's going to fall somewhere here. Let me just connect this here. Now bear in mind we said that the argument is measured away from the positive real axis. So I'm going to have theta outside here. So we can think of the small angle in here as being alpha. All right, let's go for the modulus. So we want the modulus of negative 1 minus I, which is going to be the square root of negative 1 squared plus negative 1 squared, which again is going to give me root 2. All right, pretty straightforward. Now, what about the argument? The argument of negative 1 minus I will be equal to tan inverse the imaginary part, which is negative 1 over negative 1. But bear in mind that, so because we'll get alpha by finding the tan inverse of -1/1, we also have to add, what's here? We have to add minus pi to this one. So let me write this as minus pi plus tan inverse. Well, -1/1 would still be 1. Alright. Now bear in mind that when I tan inverse 1, I'm going to get pi over 4, which is the small acute angle here. So to get the angle from the positive real axis up to this point, we actually have to add minus pi, seeing that we are going in a clockwise direction. So this becomes minus pi plus pi over 4, which is minus 3 pi over 4. Alright, and you can even look at the diagram and deduce it. So my polar coordinate would still be root 2, but my angle here, which is theta, is minus 3 pi over 4. Alright, so we'd have looked at several different quadrants, and we could actually make a summary to make this easier to remember. So when it is in the first quadrant, so I would say first quadrant, the argument of z is simply equal to tan inverse the imaginary part, which is y, over the real part, which is x. When it is in the fourth quadrant, argument of z is also equal to tan inverse y over x. Alright? Of course, in the fourth quadrant, you know, the imaginary part is going to be negative, so we have to remember that. Now, in the second quadrant, we're going to have to add pi since we're going anti-clockwise, so it's going to be pi plus tan inverse y over x. And in the third quadrant, since we're going clockwise, it's going to be minus pi plus tan inverse y over x. You can use this as a shortcut to recall how we go about finding the principal argument of a complex number. Right? Or you can simply just draw the diagram, look at the diagram, put in the acute angle, which is alpha, and then you can work out what the actual angle is from the positive real axis. Alright, it's up to you. Now, just like how we have the Cartesian form of the complex number, we have the polar coordinates that we just did. We also have the polar form of the complex number. Now let us go back to the Cartesian form. The Cartesian form is z equal x plus I y. Now my Argand diagram, as you know, z, x is the real part. So let me just put this, complete this triangle here, which is a right angle triangle. X is on the real axis, y is on the imaginary axis. Good. Here's my argument, which is theta, and here's my r, which represents my modulus. Now, from this, I could actually say that sine theta is equal to, and you know, sine is opposite over hypotenuse. I could say sine theta is equal to y over r. So I can say that r sine theta is equal to y. I can say that cos theta is equal to x over r. And of course, bear in mind that x is the real part, r is the modulus. So I can say that r cos theta is equal to x, which means that technically I can rewrite the complex number. So z becomes, in the place of x, I have r cos theta, and in the place of y, I have r sine theta. Now, notice that r is common, which is the modulus, so I can factor that out, which is going to leave me with cos theta plus I sine theta. And this is what we call the polar form of the complex number. So just like how we find the polar coordinates, r is the modulus, which is found in the same way, and theta is the argument, which is found in the same way. It's just that when we put it, if we're asked for the polar form, this is a polar form. And you already know what the polar coordinates is. If you're asked for the polar coordinates, it's just r and theta. Yeah. Here's an example. Find the polar form of -1 plus root 3i. The first thing I want to do is represent this on the Argon diagram. So I'm going to go ahead and draw my Argon diagram. -1 plus root 3i, -1 on the real axis. So let me go real, z, and IMZ. So I'm going to have -1 somewhere over there, and √3 on the positive, an imaginary axis. So about there, √3. Alright, so let me go ahead and complete my right angle triangle. Bear in mind that the argument is measured away from the positive real axis. I'm going to have theta here. Here I can put alpha. So we could probably go for the modulus first. So we know that the modulus of -1 plus √3i would be equal to the square root of the real part squared, that's -1 squared, plus imaginary part, which is √3 squared. This boils down to the square root of 4, which is equal to 2. Alright, let me go for my argument now. So my argument of -1 plus √3i, and bear in mind where this falls, it falls in the second quadrant. So because it falls in the second quadrant, whatever I get when I tan inverse the imaginary part over the real part, which is √3 over -1, I'm going to have to add pi to that. So I'm going to have pi plus. Why pi? Because we're going anti-clockwise, right? So this becomes pi. And of course, when I tan inverse √3 over -1, I'm going to get minus pi over 3, which is going to give me 2 pi over 3. Now, my polar form is z equal r into cos theta plus I sine theta. Now, bear in mind the argument, we can call it theta. So this is really theta. And the modulus refer to that as r. Alright, so r is equal to 2. So I'm going to have z equal to, open bracket, cos, my argument here is 2 pi over 3 plus I sine 2 pi over 3. So that is my polar form. Alright, and then if I want my polar coordinates, it's just r and theta. So we have the polar form right here.